So this represents all potential material on the final exam. So yesterday we went over up until, I guess this is section 2.2. Oops. So let's skip out to let's go to section 4. We'll come back to chapter 2, but let's go to section 4.5 because I don't know, didn't seem like we were everybody was understanding the stuff with the logs. All right, 4.5. Okay, so 4.5, 27, 37, 93, 95. So 27, so here's 28. So the thing to remember about logs, okay, log of A times B is log of A plus log of B for any base. Log of A over B is log of A minus log of B. And most importantly is this one. Log of A to the R, like that, is R times log of A. Again, for any base. So, but there's also some special ones like log of 10 to the R, that's just R. Natural log of e to the R, that's just R. Log base b of b to the R is just R. It's the same as this one. It's just that log base b of b is 1. And please also remember that log of 1 is 0. Okay, that one.
I have a question.
Yeah.
So why is log of 10 R just R?
The log base b of b to the R is R because the log base b is the inverse function of b to the R.
So do we just imagine there's a 10, a little 10 next to the log or something?
Usually when you just write log, you mean log base 10.
Okay.
Okay. But these one, maybe I should put a 10 there. When I write these 3 rules here, that's for any base. So log base 10 of 10 to the R is
R. Okay.
All right, so number 28, 2 times 5 plus 3 to the... All right, so solve for x. So you have to solve for the exponential first. So solve for 3 to the x plus 1 first. So divide by 2, 5 plus 3 to the x plus 1 is 50. 3 to the x plus 1 is 47. So now that you've got that, apply some log to each side. All right, so I'll do natural log. All right, and then the exponent comes down. Now here's the mistake that I saw a lot on the exam 3. People left out the parentheses. X plus 1 times natural log of, 3 to the x, oops, natural log of 3, sorry. People wrote something like that. You need the parentheses there because you have to multiply the log by the entire exponent. So if the entire exponent has more than one term in it, you have to put parentheses there because this is the 1 times natural log of 3. I know sometimes some folks in their mind's eye, they see that parentheses there, they just don't write it. But it's better to write it because it led some people to make mistakes. All right, so divide by natural log of 3 on each side. So x plus 1 is natural log of 47 over natural log of 3. So x is natural log 47 minus 1. So, and then you can pop that into a calculator and get an answer. So 47 natural log divided by 3 natural log is that minus 1, 2.5045. Okay, so solving equations with exponential expressions in them, you have to solve for the exponential expression first. Okay, so here in this equation, we solve for 3 to the x plus 1 first. Then once you do that, then you can apply a log to each side and bring down that exponent. Okay, so that's 28, and I also have...
Wait, I have a question again. Sorry.
Sure. Well,
I thought you're supposed to subtract 5 with the 50 and get 45. Because you got 47.
Oh, I have 3. Yeah, 45. Right. I was subtracting 3. So 45 natural log minus 3 here. 45 natural log divided by 3 natural log is that minus 1. So 2.4649. All right. So that was 28, similar to, so you give 27 a go on your own. And 37, so we'll do 38. So 10 over 1 plus e to the minus x equals 2. So this is one of those logistic type expressions. So again, first solve for the exponential expression. So whenever you have two fractions equal like this, or you can always do this AD is equal to BC. All right, do this cross multiplication thing. Or multiply by a common denominator or something like how we were talking about it yesterday for more complicated functions with rational expressions. But here you just have 10 is equal to 2 times 1 plus e to the minus x divided by 2. Subtract 1. Right, so we have first solved for the exponential expression e to the minus x. And then we can take a log on both sides. You can use log base 10 or you can use log base e. So I'll use log base 10 this time. Well, actually no, because this is an e here. I'm going to use natural log. Natural log is log base e, so this just becomes minus x. So minus natural log of 4 is equal to x, and that is 1.3862. Okay. So for sure we're going to have some equation with with an exponential expression to solve. Like that's definitely one question. Like I mean, like I said, I'm gonna have like a selection of problems from here, but like these two, yeah, they're gonna be there. Okay. Also, there was in 2.2 the bit about graphing piecewise functions. That was yeah 3842. So like these, that's these. You know, you're definitely going to see something like these. Why? Because those are like important sorts of things that you're going to see, important concepts that you need to understand for later on in the mathematics curriculum. All right. So also in section 4.5, you know, we've got these questions 93 and 95 about compounded interest. So we'll do 94. All right, so remember the compounded interest formula. The amount that an investment is worth after T years is the initial amount invested plus the interest rate over the number of compounding periods to the NT. All right, so R equals, so I is initial amount. T equals years. R equals interest rates as a decimal, not percentage. N equals the number of compounding periods. Per year. So number 94 asks, how long does it take or no, I'm sorry, 94 is not a great problem. So 93 is about doubling. So this is like number 93. It was 93 I signed. So like 93. So how long does it take for $1,000 invested at 3.5% compounded monthly to grow to, I don't know, 1,500? All right, so how long does it take for $1,000 invested at 3.5% compounded monthly to grow to 1,500? So when they say compounding periods, they'll say like compounded yearly, that means once a year. Compounded semi-annually, that means twice a year. Semi is half, by the way. Right. So semi-annually, that's twice a year. Quarterly, 4 times a year. Monthly, 12 times a year. Daily, 365 times a year, so on and so forth. So you want an investment to be worth $1,500, and you start.
But what about continuously?
Continuously, then it's A of t is equal to E I times E to the RT, like that. That's the,
Okay.
it doesn't fit in too well with this narrative, so I'm not really going to talk about it much. You know, you have to start talking about limits for this to make more sense. So
Okay.
I'm
All right.
really not going to ask you about that.
Okay.
So
Thank you.
$1,000, no problem. 1 plus 3.5%. So as a decimal, 3.5%. is, you got to move the decimal place over two spots. So 0.035 over 12 to the 12t, and you want to solve for t. All right, so 1.5 is equal to 1 plus 0.035 over 12 to the 12t. All right, so we solved for the exponential expression first. Now I can take a log of each side. Let's do log base 10 this time. Log base 10 of 1.5 is equal to log base 10. Oops. Log base 10 of 1 plus 0.035 over 12 to the 12t. Okay, so now that exponent comes out front. So now I can just divide out by 12 times the log of 1 plus 0.035 over 12. So log of 1.5 divided by 12 times log 1 plus 0.035 over 12 is equal to t. So let's get a number for that. So 0.035 divided by 12 is that plus 1. All right, so 1.0029166666 natural log of that times 12 divided by 1.5 natural log. So I'm calculating the reciprocal here, and then, so like when you're calculating doing a fraction on your calculator, like you can flip the fraction upside down, calculate the reciprocal. Usually calculators will have this reciprocal button right there, like this one does, this 1 over x. Just tap that and it'll give you, it'll give you the number that you're looking for. So it's 5.038 years. Is approximately t. Okay. Other sort of popular things with also 95. Other kind of popular applications of so like number 95 of exponential functions is this half-life thing. So half-life formula. So if a radioactive isotope has a half-life of h years, then an initial sample I of the isotope decays to I times 1/2 to the t over h, where h is the half-life, to an amount this much after t years. So every every half-life period, the amount reduces by half. So after h years, you get a half. After 2h years, you get a quarter. After 3h years, you get an eighth. It just keeps multiplying by half each time. But you can extrapolate that to, to however many years you have there. Folks often don't use this formulation. They use another one, like what's given in 95, but This one works just fine as far as any other just an example goes. In 95, the way they do it is fine as well. So, for example, like the half life of what? Phone's dying. Half life CD14. 5,730 years. So the half life of carbon 14 is 5,730 years. Right, so how long does it take for an initial sample of 10 grams of C14 to decay to 2 grams? All right, so we start with 10. We want to decay to 2. How many years go by in in decaying that much? So you have the half-life formulation here. The amount that's left after t years is the initial amount, which is 10 grams, times 1/2 to the t over 5,730. Okay, so in this problem, we're looking for 2 grams to be left after so many years. So we solve first for the exponential expression. And once we solve for the exponential expression, we put a log on each side. By the way, remember, you can't take the log of a negative number. So on the exam yesterday, or on Monday, I kind of saw this a lot. So it was like, I forgot exactly what it was. -3 to the x plus 1 was equal to -1 or something like that. You can't take the log of each side here because you can't take the log of -1. Right, so people reduce the equation I gave them on that exam to this, which is fine, that's correct, but you can't take the log of both sides here because you have negative number on the right. You can't take the log of a negative number. The domain of a log function is just positive numbers, strictly positive numbers. But that's fine here in this because you can just negate both sides. Right, so this just means 3 to the x plus 1 is 1. Now you can take the log of each side. Okay? So there was that. So log of 1/5 is equal to log of 1/2 to the t over 5730. So now the exponent comes down. So now I'm going to divide by log of 1/2 and multiply by 5730. So 5730 natural log of 1/5 over natural log of 1/2 is t. Okay, so we can calculate that. So 5,730 times 0.2 natural log divided by 0.5 natural log is 13,304 years. Okay. All right. So I mean, expect, some exponential equation on, on the exam tomorrow. All right. Let's go back to where we were in section 3 point. So we did 3, or not 3. We finished section 2.2. So now let's go to 2.3. It's not 2.3. I'll leave that one to you. Everyone was kind of okay with that. 2.4, average rate of change. So average rate of change, section 2.4, number 17. So like number 17 is number 19. Well, no, not that one. Number 16. So find the net change and average rate of change for f of z equals 1 minus 3z squared from z equals -2 to 0. So the net change is f of 0 minus f of -2. So always the the greater number f of 0 is subtracted. You do the greater number f of 0 minus the smaller number f of -2. Not that you do it in reverse. So f of 0 minus f of -2. Not that this number can't come out to be negative. It certainly could. So here f of 0 is 1 minus f of -2 is it's 1 minus 12, so it's -11. So the whole thing is 12. Okay, so that's the net change. So the average rate of change is the net change, f of 0 minus f of -2 over 0 minus -2. So that's 12 over 2 is 6. Okay. So the net change is just the difference in the functional values, and the average rate of change is the difference in the functional values minus the difference in the arguments. And the thing to remember about average rates of change is that if you have a linear function, the average rate of change is just a slope. Right, and the thing to remember so not the thing, but a thing, so something so if f of t is equal to mt plus b, then the average rate of change for f of t over any interval is the slope n. So linear function, the average rate of change is a constant no matter what, always the same. So in section 2.5, you've got all kinds of examples of this. So all kinds of sort of like modeling problems that go along with this. So section 2.5. So if the swimming pool. So if a water hose so if a water hose gives 3 gallons per minute of water, and a 50-gallon wading pool starts with 10 gallons of water already in it, then how long does it take for the hose to fill the pool the rest of the way? Right, so the amount of gallons of water in the pool. So anytime you've got a rate of change problem in which the rate of change is constant, and somehow the problem will let you know that the rate of change is a constant. So in this one, I said, okay, this water hose, it gives 3 gallons a minute of water. So that's, and I didn't say it varies, it just gives 3 gallons a minute of water. Okay, so it's a constant. So because the rate of change three gallons per minute is constant. I'm sorry, guys, just have to give me. So because the rate of change 3 gallons a minute is constant, the number of gallons in the pool at t minutes is g of t 3t plus, and what was the initial amount? 10. All right, so constant rate of change. So rate of change and initial amount. All right, so the y-intercept in the linear function, when you're talking about some kind of rate of change or some kind of applied type problem, the y-intercept can also be thought of as an initial amount. Okay, so the amount of the function, the value of the function at time t equal to 0. All right, so it's a 50-gallon pool. So we have a 50-gallon pool, so we want 50 gallons. And how long does it take to go from 10 to 50 gallons? So 3t plus 10 gallons at t minutes needs to be equal to 50. So 40 is 3t. So 40 over 3 is t. So that's 13 and a third minutes is t. All right, so linear functions with these kinds of applied problems. So linear functions have come up a lot, of course, because it's just dealing with things that have a constant rate of change, which happens all the time. Driving at a constant rate of speed, water coming out at a constant rate of speed, working on mowing a lawn at a constant rate of speed, and all these different things. Okay. So that was 2.4. 2.5, I mean. 2.6. 2.6 on. Oh, I think we're okay with that. Let's leave 2.6. Let's go on to 2.7. 2.7 is on combining functions. So on function composition, so number 57 in 2.7. So we'll do 58. So we have f of x is equal to 2 over x. G of x is equal to x over x plus 2. Find f following g, g following f, f following f. So this is function composition, right? And the way these are defined, right, f following g of x is the function f of g of x. And what exactly does this mean? Well, g is this, x over x plus 2. Right, so you can think of it that way, or like what is f? F is f of x. F of x is 2 over x. Right, so if f of x is 2 over x, f of g is 2 over g. Right, f of x is 2 over x. F of z is 2 over z. F of t is 2 over t. F of g is 2 over g. So in this case, f of, whatever you're putting in here, you just put it down there. You replace every instance of x with g. Right? F of x is 2 over x, so f of g is 2 over g. But we also have this other symbol right next to it. Which is fine. So what was g of x? G of x is x over x plus 2. So this becomes 2x plus 2 over x. So 2x plus 4 over x. So that would be f following g. G following f. Right, so what is g? G of x is x over x plus 2. So g of f is f over f plus 2. What's f is 2 over x. So that's fine as an answer right there. But if you want to simplify the expression, you can take it further. So this becomes 2 plus 2x over x. And so these guys cancel, and you get 2 over 2 plus x, 2x. So that would be the simplified expression, although this is an acceptable answer as well. All right, so notice that f following g is not the same as g following f. It's a completely non-commutative operation, function composition. And you could also take the composition of a function with itself. F following f of x, that's f of x. F of x is 2 over x, so f of f is 2 over f. So that's 2 over 2 over x. All right, so that is just x, actually. So this means that f is its own inverse function. And then g following g. So it was g was x over x plus 2. So this is g over g plus 2. So if you want to simplify this, you have to first add on the bottom. So x plus 2 times x plus 2 over x plus 2 is equal to, so 2x plus 4, so this is 3x plus 4. So as a simplified expression, that's what you get here. Okay, so for function composition, although, I mean, on the exam, you can always just leave the unsimplified expression. I'm fine with that, if I ask such a question.
I have a question.
Yeah.
So if you ask this type of question on the exam, do you also want us to like state the domains or no?
If I ask for the domains, then yeah, but I don't think I will. We've talked enough about that. So, what the domain of various functions are. And I could ask a question about that, like what's the domain of this function? Right, we went over that in section 2.2.1. We did some of those yesterday. I don't want to keep asking the same thing over and over again. But, in the book, they have these practice problems, and they want to make sure the problems are thorough. So. All right. It's 2.7. 2.8, remember the 2.8 is about the inverse function. So in section 2.8, now, of course, not every function has an inverse function. The graph of the function, so the function needs to be 1-to-1. In other words, the graph of the function satisfies not just the vertical line test, but the horizontal line test. And please, guys, when you're drawing graphs of functions, make sure they satisfy the vertical line test. All functions satisfy the vertical line test. So don't make drawings that look like this. Okay, that doesn't satisfy the vertical line test. Right? Be careful about how you draw things. Take a moment and use your pencil in a careful fashion to get a decent drawing. Also, the functions that we've been looking at, polynomials and rational functions, they're always smooth. Okay? They're always smooth. There's no sharp corners. This sort of thing doesn't happen. The only function we've seen that has a sharp corner are piecewise, that could have a sharp corner, are piecewise functions. Or like the y equals the absolute value of x looks like that, and that has a sharp corner. Okay, but polynomials, rational functions, exponential functions, they never do. They're always nice and smooth. So, all right, so that was just a side note. So here in 2.8, finding inverse functions, you have to be a 1-to-1 function. So let's see, 49 and what did I have there? 49 and 57. So one type of function that always has an inverse function is a linear function. So f of x is equal to 7 minus 5x. Find f inverse of x. Okay, so what you do is you write y equals 7 minus 5x. Exchange x and y. And now solve for y. So x plus 7 is minus 5y. Divide by negative 5. So that's your inverse function. If you don't want to write it like that, negative 1/5 x minus 7/5. Okay, the slope, so with a linear function, its inverse is a linear function, but the slope is not the perpendicular, by the way. Okay, total confusion about that. All right, you know, we talked about two lines being perpendicular. That's when the slopes are negative reciprocals of each other. Okay, here this line has slope -5. This line has slope -1/5. They're not perpendicular. Okay, like the line of slope like 2, a line of slope 2 would be like this. A line of slope 1/2 would be like that, not perpendicular. They're both positive slopes, they can't be perpendicular. These two, they're both negative slopes, they can't be perpendicular. Slope -1/2 is perpendicular, but that's not the inverse function. Okay, two different concepts, completely different. Other type of function that has inverses are also these Moebius functions. So 58. So 4x minus 2 over 3x plus 1. No, I don't think I like this one. No, that's an awful example. So this is like 57. Let me try a different one. There we go. Okay, so f of x is this. So a linear polynomial divided by a linear polynomial. That always has an inverse function. It's called a Moebius transformation. So you write y equals 4x plus 5 over x plus 1. Switch x and y. And then solve for y. So solving for y here is a little bit trickier. So what you do is two of the terms have y's in them, and two of the terms don't have y's in them. So you move the term with y to one side, and the terms without y to the other side. Factor out y on the side that has it, and then divide. So that's f inverse of x. Other type of function that has inverse functions are exponential functions. The inverse function of an exponential function is the log. Most other functions don't normally have one, although you can restrict the domain so that it does. All right, so that's 2.8, chapter 3. What time we got? 10:42. Good, we got some time to talk about chapter 3. So I was really upset about the problem I gave you on the exam about finding the maximum area business. I did that one as an example in class the day before the exam, and we had a homework problem very similar to it, but I don't know. Well, we didn't get it. So quadratic functions. So if you have f of x in standard form, is a times x minus h squared plus k. The graph of this thing looks like this. Right? It's a parabola. right, whose vertex is h comma k. So that's if a is bigger than 0. If a is less than 0, then it's the downward facing parabola, where the vertex again is hk. And given f of x equal to ax squared plus bx plus c, the h is minus b over 2a, and the k is f of minus b over 2a. So, you can get from here to here by completing the square. Or you can go from here to here by completing the square, or you can just use these formulae here. So now when the parabola faces downward, the vertex there, that is a maximum value for the function. And when the parabola goes upward, it's a minimum value for the function. So that allows you to do these max-min problems, that deal with quadratic functions. And, we had several of those. There was a thing about the rain gutter on the homework, and everybody did kind of all right with that. And there's a thing about fencing the horse corral. It seems like folks were doing all right on the homework, and then I asked this question, on the exam, and I just didn't get what I was looking for. So, let's go over it again. So 500 feet of fencing material is used to create a rectangular pen in the shape shown, with 3 compartments. In the shape shown. Find the value of x that maximizes the area of the pen. And then what is the max area? All right, so if this is x right here, then the area, that's the height of this thing, and then the area is going to be x times L, where L is the length of this thing. These guys don't enter into the area calculation. They're just there to separate the fenced-in rectangle into different pens there. All right, different compartments, I guess. All right, so, but what these X's do is that they use up fencing material. Okay, so we have 500 feet of fencing material. Right, 4 lengths of X plus 2 lengths of L are going to be used to construct this pen. So then 500 minus 4x is 2L. So 250 minus 2x is L. So L can be written in terms of x. So now the area is the length times the width, is length times x. Okay, so I wrote the length in terms of x, and I was able to do that because I know I've only got 500 feet of material to work with. All right, so 500 is 4x plus 2L, and that's all these separators do, is they separate the pen into compartments like that and take up fencing material. But as far as the area calculation goes, the extra bit, I mean, I could have a whole bunch of these things. They just take up more material, but they don't affect the area. So the area is length times x. So the area as a function of x is 250 minus 2x times x. So this is a quadratic function. right? So that's the area of the pen, right? So the max area occurs at the vertex. Right, so the max area occurs when x is equal to h, which is minus b over 2a, so that's minus 250 over 4. So that's 62.5 feet. Right, so at 62.5 feet, we get the maximum area for the pen. Right, and then the max area itself is a of 62.5. I'm going to plug it into this one. So that's 125 times 62.5, which is 125 times 62.5, so 7,812.5. Right, same kind of problems we've been doing. All right, so this is very typical of a max-min problem that boils down to a quadratic function. Okay, in Calc 1, when you get to Calc 1, you'll do more max-min problems that don't just deal with quadratic functions, cubic functions, whatever else kind of functions. Functions of the form 1 over x, functions with reciprocal expressions in them, rational expressions. So once you get to calculus, you can do a lot more different types of things. But here it's just quadratic, so there's a fewer examples, but there's this box type thing is a typical example. So the one about the rain gutter, number 64, that's another one of these rectangular examples. You're making this rectangle out of 30 inches of aluminum, and you're only using 3 sides rather than all 4 sides. So just varying the number of sides is kind of like how you get different problems out of that. Okay, so rectangles with 3 sides. You have a rectangle, but then you add more sides to it or take away some of the sides. I could say, oh well, one side of this pen is built along a barn or something like that. All right, so you got this barn here, and then I'm going to build this pen along here like that. Right, so now the amount of fencing material used isn't 4x plus 2l, it's just 4x plus l, because I only need one side of length l. Right, but as I stated it, it looks like that. Okay. Let's do one graphing a quadratic function. So sketch the graph of f of x equals x squared plus x plus 1. Well, let's do a different one. 2x squared plus 7x plus 8x plus 1. Label clearly all x and y intercepts. Okay, so you can basically you need to find the vertex of the parabola and then graph it, right? So you can do that by completing the square, or by using the formula we had before. So let's do it this time by completing the square. So So, but first of all, before that, the y-intercept is right there. It's 1. Okay, it's the constant term in a quadratic function. Okay, so the y-intercept of any function f of x is f of 0. It's where the x is equal to 0. In this case, it's 1. So the y-intercept is 1. And then the vertex will complete the square. So fx is 2x squared plus 8x plus 1. So this is equal to that. So you factor the coefficient out from the first two terms, and then you complete the square on the inside of this first. So 4, you divide by 2, you get 2. Square it, you get 4. So you're going to add 4 here. And then on the outside, you got to subtract 4. Well, it's not 4. It's 2 times 4, right? I mean, we added a 4 inside here, so it's multiplied by 2. So we actually added 2 times 4. So we subtract 2 times 4 here, plus 1. So we get 2 times x plus 2 squared, minus 8 plus 1, minus 7. And so there it is. So the vertex is at h comma k, so it's minus 2, minus 7. So minus 2, minus 7, and then the x-intercepts are where this is equal to 0. Where this function is equal to 0. So 2 times x plus 2 squared minus 7 is 0. So basically you're going to have x is equal to minus 2 plus or minus the square root of 7 halves. So square root of 3.5. So x is minus 2 plus the square root of 7 halves, and minus 2 minus the square root of 7 halves, both of which are negative numbers. So if you want to graph it now, the y-intercept is at 1. Well, we're going to have to do this like that. So then minus 2 minus 7, maybe like right about here. So here's minus 2 minus 7 down here. And there's the y-intercept there. So there you go. Something like that. And again, parabolas, they're not wobbly. So, I mean, I made a little bit of a wobble in this one. But, you know, you try to keep it to a minimum. And they're nice and symmetric on each side, so I'll just leave it at that. All right, so there's the y-intercept at 1. How did we get the y-intercept? The y-intercept for any function f of x is just f of 0. So here's f of x. Y-intercept is f of 0. Oh, I'm sorry, it's time to go. And then, you know, with this one, you have the x-intercept shown. Of course, sometimes quadratic functions don't have roots within the real numbers. You know, in which case the parabola will be up here, or it'll be down here, or something like that. Above the x-axis completely, or below the x-axis completely. All right, guys. So I'll be in the WebEx room at 11:30. So you can come and see me today if you'd like. Otherwise, I'll see you tomorrow. Okay. Have a good afternoon.